what I will do, I will initiate and then give a little.
Sir, your voice is very slow.
Yes,
Can you hear
sir.
me clearly now?
So we are on live now, and I think we should start, if you permit us.
Can you hear?
Yes, sir. Now you are audible.
Okay.
If you permit us, then shall we start?
Yes, you start.
Okay. A very good afternoon to all of you. On behalf of Manipal University, Jaipur and Professor Pierre Sharma Memorial Educators Association, myself Alok Bhargav, welcome you in this event of memorial lectures on birth anniversary of our teacher and torchbearer, late Professor Pierre Sharma. Today, we'll have three distinguished guests with us. Professor P.N. Pandey, the Dean of Gram Bharati University from Allahabad, Dr. Anirban Chaudhary from UK, and Professor O.D. Makinde from South Africa. We are highly obliged that they have accepted our invitation in a very short span of time, and will have their words in the later session of this event. Now, I would like to invite Professor Anup Kumar Mukhopadhyay, Dean, School of Basic Sciences, Manipal University, Jaipur, to welcome our guests and participants of the event. Dean, sir, please.
Good afternoon, everybody. This is a great occasion. At the very first instance, let me put my homage to great Professor Sharma. I think it is academicians like Professor Sharma who are not only torchbearers, who are creators of fields, and particularly in the field of fluid dynamics, his contribution is not only immense, but also in a very variety of modes. He has developed students, researchers, and academicians of next and next and next generations. We have few of them, and we are very proud that we have few of them as our colleagues, like Dr. Bhargava, Dr. Sharma, and many others. And it is what happens that when a legend, passes through his journey, he goes on contributing to the society for societal causes, to the academia for academic causes, and to the research for research causes. And very seldom we will find somebody like Professor Sharma who is contributing in all the three aspects. As well, he was a fantastic person, as I come to know from the colleagues here. Unfortunately, I didn't have a chance to personally interact, but from the magnitude of his work, as I was supposed to look into, and I'm simply amazed. There cannot be a word more than that. He's an amazing academician and great teacher, great researcher, and it is really beneficial for us that we are taking this occasion to put his not only memory but his work across to the younger generation of people. And I believe that I should definitely congratulate all our invited speakers who have taken our invitation, and today's participants, they will immensely gain from their the deliveration today. I would also like to express our sincere gratitude and warm welcome on behalf of Professor K. Ramnaran, Chancellor, Manipal University, Jaipur, Professor E.K. Prof, President, Manipal University, Jaipur, Professor N. Sharma, President, Manipal University, Jaipur, Registrar Professor H. Vishakar Kama, and Professor Jagan Karod, Dean Faculty of Engineering. The entire media team welcomes the invited speakers and all the participants. And our special thanks goes to Professor Kalpana Sharma and Professor Alok Bhargava, and Siva Kumar, of course, the head for organizing this particular webinar on the occasion of birthday of Professor Sharma. And I believe that Yes, Bharti is something very special celebrity. But for people like Professor Sharma, every day their student does some work. Their student does some work. He is born, and he will continue to be born and be born in infinite number of days to come. And we all pay our homage by doing good work, good research, good fluid dynamics work, and dedicate that to the academia and to the research work. Much after we are gone, our work should remain and should be highlighted, and thereby the whole world should be remembering what has been the contribution of Professor Sharma. Coming to the Faculty of Science, School of Basic Sciences, it was supposed to be, put before you by our director. Unfortunately, she is here today. On way on her behalf, the regards and best wishes for organizers and to the invited speakers and to the participants. The School of Basic Sciences started its journey in the year 20. We are only 9 years old and we are already a A plus university, first private university of Rajasthan. We have 5 departments: the Department of Biosciences, Department of Chemistry, Department of Computer Applications, the Department of Mathematics and Statistics, which in particular is doing the webinar today, and also the Department of Physics. All the departments are equipped with state-of-the-art laboratories, dedicated faculty. Uh, Out of our about 70 faculties, more than 90% are PhD qualified and postdoc qualified from abroad and IITs and places like that. And we're very proud of it. And all our teachers are very dedicated to the development of the students, and our research scholars are all trying. They are doing wonderful job, and I guess that in days to come, they will be more and more and more glories to the department. Particularly, this department of mathematics and statistics is contributing immensely in terms of to the world of academia, and I wish them all the best for continuing to do so. We have already, more than 4 crore of fund, which is something that we're really proud of, and we are still continuing to get, funding from many external agencies. And in this regard, I would appeal once again that uh, our physics department is now coming up in a big way, and they should continue their journey. And particularly, the Department of Physics also has industrial projects. The Department of Biosciences has very high value projects supported by Department of Biotechnology and Department of Science and Technology, uh, Structural Engineering Research Board. So that way, and our Department of Computer Applications, which is 1 year old, has got very good placement in the industry. So overall, our faculty of science is doing nice, and our publications are also in very high value journals, high impact factor journals. So that way, the faculty is contributing for the development of science in the country and in the world as a whole, and we take pride in that. And with I would once again thank the organizers for giving me this opportunity to present my views on this occasion. Once again, I pay my homage to Professor Sharma on this occasion. Thank you once again, one and all. Thank you. Bye bye.
Thank you very much, sir. Now I request to Dr. Indiva Kumar, Head of Department of Mathematics and Statistics, Manipal University, Jaipur, to address the gathering. Indiva, sir, please.
Thank you, sir. A very good afternoon to all present here. It gives me an immense pleasure to welcome today's guest, Professor P.N. Pandey, and speaker Professor O.D. Makinde and Dr. Anirban Chaudhary. I also welcome our Dean, Faculty of Science, Dr. Anup Kumar Mukhopadhyay, Director, School of Basic Science, Dr. Lalita Lindwani, faculty member of the department, and my dear participants. We assemble here through digital platform on the occasion of memorial lecture on birth anniversary of late Professor Pierre Sharma. On behalf of the Department of Mathematics and Statistics, as a head, I would like to say a few things about the department. The department was established in 2011. Department offered 3 programs: UG program, BSc Mathematics Honours, PG program, MSc and PhD program. BSc Mathematics Honours and MSc program are based on CBSE, so that a student will have a choice to choose a course which they are interested. The department is committed to offer knowledge not only in theoretical course but also in courses of applied nature, including mathematics and statistics, to assess the health of a crop, economic growth of a country, even to predict the impact of current pandemic situation in future data analysis. In particular, statistics plays a vital role. Realizing its importance, we kept around 40% courses from statistics in the curriculum. We have well-equipped lab facilities with software like SPSS, R, AMOS, Manipal, Statecraft, etc. to provide hands-on training to our students. With 22 qualified and experienced faculty strength, faculty members are actively engaged in teaching as well as in research in the field of operation research, information theory, theory of sample survey, reliability theory, spatial function, algebra, fluid dynamics, and celestic mechanics. With this, I once again welcome to all the participants. Thank you.
Thank you, sir. Now, I would like to invite Dr. Ruchika Mehta to introduce the video of life journey of Professor Pierre Sharma. Dr. Ruchika, please.
Ma'am, please on our mic.
Now it's fine?
Yes.
Okay, thank you, sir. Should I start?
Yeah, ma'am, please.
Professor Pierre Sharma, a very simple and high-thinking personality, served in the Department of Mathematics, University of Rajasthan, Jaipur, from 16 February 1978 to 9 July 2016. Professor Sharma obtained his PhD degree in the field of fluid dynamics from University of Rajasthan in 1985. He contributed to the field of fluid dynamics by his outstanding research work. He is a recipient of several awards from many organizations for his extraordinary capabilities and research work. Besides the academic and professional excellence, he has contributed a lot for the betterment of society. Though his physical presence is highly missed, but his memories and his work will always remain with us. So in memory of Sharma sir, we are playing a small video of his journey. I request Dr. Vivek, please play the video of Sharma sir. Vivek sir, please.
Thank you, Vivek sir. Now, I would like to invite Dr. Pooja Sharma to introduce our invited guest, Professor P.N. Pandey. Pooja ma'am, please.
Thank you, sir. Good afternoon to all participants and guests. Myself, Dr. Pooja Sharma, student of Professor Pierre Sharma, sir. Currently, I am working as a Deputy Director Research and Associate Professor in Department of Mathematics and Statistics, Manipal University, Jaipur. I hearty welcome to all of the participants and guests over here. It gives me immense pleasure to invite Professor P.N. Pandey, sir. Presently, he is working as the Vice Chancellor of Nehru Gram Bharati University, Prayagraj, Uttar Pradesh. Previously, he has worked as a professor and head, Department of Mathematics, University of Allahabad. He has more than 100 research papers published in reputed journals. He is the founder, General Fellow and General Secretary of International Academy of Physical Sciences. He is very close friend to Professor Pierre Sharma, sir. I hearty welcome to Pandey, sir. I request you, sir, kindly bless and share few words with us. Pandey, sir, it is over to you. Pandey, sir.
Pandey sir, please unmute yourself.
Okay,
Yes,
thank
sir.
you, Pooja.
Thank you, sir.
Professor Mukhopadhyay, Dean Faculty of Science, Professor Lalita Lidwani, Director, School of Basic Science, Dr. Indivar Kumar, Head of Mathematics and Statistics Department, Dr. Kalpana Sharma, Dr. Pooja Sharma, Dr. Alok Bhargav, Dr. Ruchika Mehta, Dr. Vikas Singh, other faculty members of Manipal University, invited speakers, Professor O.D. Makinde, South Africa, Professor Anirban Chaudhary, United Kingdom, Dr. Pramod Gaur, and other participants. Good afternoon to all of you. I am pleased to see you all at the birth anniversary of late Professor P.R. Sharma, who was my close friend. Born on July 10, 1956, Professor Sharma obtained his BSc, MSc, MPhil and PhD degrees from University of Rajasthan in 1975, 77, 78 and 85 respectively. He secured first position in MSc examination of the university. He did his PhD work on some flow problems of non-Newtonian fluids with special reference to heat transfer under the supervision of late Professor P.D. Verma. He started his teaching career from University of Rajasthan as assistant professor in 1978 and was elevated to associate professor and professor in the Department of Mathematics thereafter. He served the University of Rajasthan in various capacities such as member of Senate of University of Rajasthan, member syndicate, dean Faculty of Science, director Vigyan Bhavan, head Department of Mathematics, member Academic Council, rector and principal of University Maharaja College, and served several administrative posts. Besides a successful administrator, he was a very successful teacher and a good researcher. He contributed significantly to fluid dynamics, boundary layer theory, biofluid dynamics, MHD, porous media, heat transfer and operation research by publishing 185 research papers in journals of international repute. He supervised 34 PhD and 30 MPhil students. I fully remember when I met Professor Sharma in 2006 for the first time and was attracted by his magnetic personality immediately. After that, I invited him to deliver a lecture in the Conference of International Academy of Physical Sciences at Guru Ghasidas University, Bilaspur in 2007. His son, Dr. Pramod Gaur, was also with him. After 2007, he became a life member of IAPS, International Academy of Physical Sciences, and participated in each and every conference of the Academy in different capacities. Since then, he served the International Academy of Physical Sciences as a secretary, a vice president, acting president for some time, and as an executive counselor. He was honored with the prestigious fellowship of International Academy of Physical Sciences in 2015, apart from other distinguished awards to his credit. His services to the IAPS are unforgettable. Due to his inspiration, Jaipur became the city of maximum life members of IAPS in whole India. His wish to open a local chapter of IAPS in Jaipur could not be fulfilled during his lifetime because of some constitutional constraints. By his personal efforts, the difficulties were removed in 2018. Now we will try to fulfill the same with the help of Professor Pierre Sharma Memorial Educators Association and the Manipal University faculties. He was a very good organizer and a man of iron determination. He organized two international conferences of the Academy in Jaipur University. In first conference, his colleagues were pressing him to talk to me that due to unavailability of funds, it is not possible to organize the conference. He told me hesitantly, what should we do? I said that God will help us in organizing the conference. Then he told me, okay, we will organize the conference, and with his great efforts, the conference was organized successfully, which was attended by maximum number of participants in the history of conferences of IAPS. He was a great mathematician, having contributed a large number of research papers in different fields of mathematics. And not only this, he was the author of many successful books. I think Professor Sharma was a good academician, an able administrator, and above all, he was a noble man. He was very much affectionate to his students. In his memory, his students formed an association to remember him. This shows the devotion of his students towards him. It was the wish of his students to organize a big conference in his memory, but it could not be possible due to the pandemic COVID-19. I hope that it would be possible next year. With these words, I pay my tribute to my dearest friend, late Professor Pierre Sharma. And I hereby launch the website of Professor Pierre Sharma Memorial Educators Association and congratulate the members of the association. Thank you. Jai Hind.
Thank you very much, sir. We can see the website page.
Thank you.
Thank you very much, sir. Thank you, Dr. Vivek, providing us this live part. Now, I would like to invite Dr. Vivek to introduce our invited speaker, Dr. Anirban Chaudhary. Dr. Vivek, please.
Yes. Good afternoon, ladies and gentlemen. It is a great pleasure for me to introduce our respected speaker, Dr. Anirban Chaudhary, sir, today. He did his PhD in the mechatronics from the Center of Mechatronics at IIT Kanpur, India. Currently, he is a professor in the Computer Science and Artificial Intelligence School of Computer Science and Electronic Engineering, University of Essex. He is also a member of Smart Health Technology Group and the Robotic Groups at the University of Essex. Prior to the join at the UAE, he was a postdoctoral research associate at the Northern Ireland Function Brain Mapping Facility at Ulster University, Northern Ireland, UK. Dr. Chaudhary has contributed to UK India, the Atomic Partnership Project funded by the British Council, UK, and the Department of Science and Technology in India. He is also led to successful completion of two clinical trials on the post-stroke robotic assisted neuro rehabilitations, one in the India and the other in the UK. Dr. Chaudhary has the expertise in the area of robotic rehabilitation, brain computers, interface, assistive technology, human robotic robot cooperations, and autonomous mobile robotics. He has published the several journals papers in the top journal of the field, including Transactions and the Journal of IEEE and LJBS. So now inviting our respected speaker, Dr. Anand Chaudhary, sir, for the invited talk.
Thank you, Vivek, for such a nice introduction. And I say a very good morning. This is a good morning here and good afternoon to you all for organizing this great event in the occasion of in the memory of late Professor Pierre Sharma, whom I know from my good friend, Dr. Pramod Gaur, who was a friend and colleague here at Ulster University during my PhD and my postdoc. So having said that, I'm going to my presentation. So let me share my screen first. Is it visible?
Wait, sir. Visual. Wait.
Okay. Yeah. So today my topic of talk is computational modeling of for brain-computer interfaces for hand exoskeleton. Sorry, hello.
No, not say.
Is it audible?
Audible, sir, but not say the PPT.
Okay,
No,
just a
no.
minute. Okay. Share screen. Yeah, now is it visible?
Not.
No, sir.
Also.
Is it okay now?
No, sir.
Oh, I don't know. It's showing some bad network quality.
Yes, yes, sir, showing, sir.
Yes, sir.
Showing. Oh, okay,
Now it is
that's
open.
great. Okay, thank you. So today my topic of talk is computational modeling for brain-computer interfaces for hand exoskeleton-based rehabilitation therapy for stroke patients. So yeah. So here are the following topics which I will be talking about in this presentation. First of all, I will introduce the brain-computer interface. What is that? What purpose they solve, and some examples of existing brain-computer interfaces. And as these brain-computer interfaces run basically on the brain signals or EEG signals, then I will explain how to decode these EEG signals. Then why do we need BCI for neuro rehabilitation systems? And then I will come to hybrid BCI designs. Then exoskeleton-based hand rehabilitation systems for stroke patients and corticomuscular activations, which is a new trend in neuro rehabilitation. So first of all, what is brain-computer interface and what its relation with the rehabilitation of stroke patients? So first of all, our brain, as we know that our brain controls everything, every motion in our body. But how does it do so? So first of all, we should know that in our brain, there is a map of all our limbs, right from our legs to hand and mouth and etc. So if we look at this map, which is called homunculus, which is a map of our brain's motor cortex. So we have this motor cortex and the somatosensory cortex. These two cortex, these two brain areas are basically responsible for all the movements and the sensations in the body. So what we do here is basically signal processing. So a lot of computational modeling techniques go into this. So there are a lot of mathematical and statistical techniques, such as Fourier transform and bandpass filtering and all. So there are a lot of different brain signals, such as EEG signals, which is very popular because it's non-invasive. So you don't need to insert anything inside the brain. So you can use some electrodes on your brain scalp and acquire the signals from there only. So after the acquisition of EEG signals, we apply some signal processing techniques to extract different features out of it. And then we use some machine learning and pattern recognition algorithms to classify these signals into different motor activities, like left hand motion versus right hand motion, or you can also type using your brain signals, which is amazing because you don't have to like use your fingers or any other limb to do that, or it's not even speech to text converter. You just you can think in your brain, concentrate on a grid of letters, and as you concentrate onto it, there is a technique to find out that on which letter you are concentrating, and thereby you can select those letters to type your sentences. Also, this technology can be used to rehabilitate the stroke patients. So as you know that when a patient is affected by stroke, he loses his limb movements. So we take them to our physiotherapist who do some kind of physical therapy on their hand or feet, and thereby they gradually learn those motions. But instead of taking them to the physiotherapist, we can apply brain-computer interfaces and extract their movement intentions directly from the brain. And because they cannot move their fingers or hand, we can use a robotic device to move their fingers, which will be controlled by the brain signals. So there are several applications of this technology. First of all, we can replace the ability of a person who is disabled. Like if somebody loses his lower limb movement, then we can use this technology to control the wheelchair motions. We can also use this technology for supplementing the motor movements. Like if you have partial disability, then the robotic devices can be used to compensate your ability. It also works as a passive BCI, which is used for monitoring your psychological state. Suppose you are driving and you are falling asleep, then this kind of technology will make you alert by observing your brain states. So there are several different applications of this technology. So now I'm going to show some examples of existing brain-computer interface technologies. So this is an old work conducted by our previous team in 2010. It is one of the earliest BCI designs for stroke rehabilitation. So what we had done here was that we controlled a computer game. So this computer game, which you can see here in the bottom left and bottom right side, that you can see a ball which is falling from the top of the computer screen to some location at the bottom, like green and red. So here green is the target and red is the non-target. So you need to think the ball. You need to think that the ball should fall on the target. So you need to imagine the left or the right hand motor imagery, which is basically imagination of your left or right hand movement. And based on your imagination, the ball will gradually shift towards left or right and ultimately falling to the target basket. So this is a typical diagram for the brain-computer interfaces, where we take the signal, we do some signal pre-processing techniques, and then we do the feature extraction and classification, and ultimately we send the command signals to the computer. Here is another example where we are controlling a robotic arm for disabled patients. So this experiment was conducted in IIT Kanpur. Basically, it was done in Regency Hospital, Kanpur, where we gathered some stroke patients and asked them to wear this robotic device on their impaired hand. And then we took the EEG signal from their brain and we processed it online in real time in a computer. And then we send them commands to the to this robotic hand, which ultimately help them opening their fingers, which they cannot do otherwise because they are disabled by some kind of stroke. So as I play the video, you can see how it works. So first of all, the patients were shown image of a hand to instruct them to start thinking about that motion, like opening their fingers. Then we gather the signal from their brain, and then we process it online, and we send the commands to the motor. So you can see that as he concentrates on opening his fingers, the robot is gradually opening his fingers and also showing some kind of visual feedback on the computer screen. So you can see a virtual hand moving on the computer screen here. Next, another example I would like to show you is how to type using these brain signals. So you can use these brain signals to select some letters out of this letter grid. So you see that there is an instruction to write this word hands free. So please look here how this patient is actually concentrating on different letters. So you are seeing that the row and columns of this grid are alternatively blinking, and there is a signal called P300 signal, which works in a way that when you focus at some target, then and the target appears, then there is a certain signal in your brain after 300 millisecond of the issue of the target, and we captured that signal, and then we would be able to determine on which letter this person is focusing. So this is a typical example of how the EEG signals looks like. So there are, I have already said that there are a lot of mathematical and statistical techniques which are used to decode these signals, because as you see that by visual inspection, you can't really figure out what these signals are telling you. Unlike the EMG signals or the muscle signals, which are very very easier to decode because of the change in amplitude in a large amount in those signals. These signals do not change amplitude so much. However, their band power can change depending on which frequency band you are looking at. So lot of filtering techniques go on to decode are applied to decode these signals. So these are all the different channels, EEG channels, F3, P3, P4 and all, which acquires the signal from the neurons. So you can see these neurons here. And you know that in our brain is composed of billions of neurons which are interconnected with them, and they pass some electrical current between one another. And when these currents are passed, these currents can be recorded. These electrical potentials can be recorded on through an electrode which sits on the top of the scalp actually, not the skull. Okay, so how do we decode this signal? Is that first of all we have a particular band of frequency which is called sensory motor rhythm. These are oscillations in the brain at a particular frequency range. So this frequency range is between 8 to 30 hertz. And as you see that there is a power spectrum graph. There's two power spectrums, one in top and one in bottom. So when we are not doing any activity, we can see a middle line here, which is above the threshold, which is in the red zone. Now, when the patient concentrates on moving the fingers, this red line goes down towards this lighter region. So there is a drop in the band power. Of within this frequency band, and basically we need to see this change in the band power. So if you see the graph in the right hand side, so there is a baseline period, and after the baseline period we show them some cue to instruct them to concentrate on their hand motion. And as they concentrate on the hand motion, you can see there is a drop in the signal power, which we called event related desynchronization. So you see that the movement related ERD is falling down, and then there is a rebound. So what is this rebound? When we stop thinking about that hand motion, the signal amplitude again comes back to normal and beyond. So which is called rebound. It typically happens in the region of beta band, 16 to 24 hertz. And this desynchronization, that is the decrease in the signal, that is happening at mu band between 8 to 12 hertz. So next, I talked about the P300 signals, which is a signal through which you recognize something. So I typically give one example, like you are standing in a cycle stand or a car parking, and you suddenly see you are searching for your car or your cycle or motorcycle, and suddenly you identified your car or motorcycle. So this identification generates a spark in your neurons. So this sudden rise in potential is called P300 signal. So there is a gap between 0 to 300 millisecond, um, uh, like the appearance of this signal and the stimulus that is given to you. Stimulus means your identification, your consciousness of identification of your object. So this signal P300 is recorded, is identified by some computer algorithms, and then it is channelized to print the letters on the computer screen. Now coming back to the stroke rehabilitation, for which this application is typically used. So there are several different traditional techniques of stroke rehabilitation, such as mirror neuron therapy, where we put the hand of a patient inside a mirror box, where he gets the reflection of his able hand, and gets the feeling that while moving his able hand, the disabled hand is also moving. So it's kind of a it sends some it activates the mirror neurons in the brain, which helps in rewiring the brain. So our brain never stops learning, basically. So previously it was known that our brain stopped rewiring itself after a certain age. But right now the current knowledge is that our brain never stops learning, and at any age you can basically learn, and the neurons are capable of facilitating that. So when you lose your hand movement, it basically some wiring in your brain gets broken, and you can rebuild those connections through practice. But this practice needs concentration and engagement, which is provided by the brain-computer interfaces. So several techniques are used for that, such as neurofeedback techniques. So there could be some visual feedback, like here you can see a gradual motion of a hand, and also the exoskeleton motions, which overcome some limitation in the conventional therapy. So typically the limitations in the conventional therapy are several, like they are passive in nature and not challenging enough for the patients. And also you can see that there is a lack of medical professionals or therapists in our society. So these kind of automated robotic devices can provide an alternative for a human therapist, and it can perform the therapy for you anytime. So there is a rise in the intensity of the therapy, and thereby patients can get advantage. So in recent years, we also developed some new techniques to design advanced brain-computer interfaces, merging the brain signals with the muscle signals, and we called this technique as band power correlation. So it's typically a Pearson correlation technique, but followed by some signal processing steps, which enables it to detect a specific signal. And there is some assistance as needed technology for hand exoskeleton. So these are control techniques, control system design techniques, which are used for the control of hand exoskeletons. So first of all, I would like to discuss the this technique called corticomuscular coherence, and what it does is that it fuses the brain signal with the muscle signal. So as we know that coherence is a typical phenomena which is occurs in physics when different types of signals communicate with each other. So here we have two signals, EEG signal and EMG signal. These two signals also communicate with each other and sends the brain commands to the hand or other limbs. So if you look at the coherence spectrum here between 5 Hz to 35 Hz, you can see a rise in the signal in the coherence amplitude between 20 to 25 Hz. And this rise in the coherence coefficient is actually identified by the brain-computer interface algorithms to generate some kind of robotic motion. So now little bit into the mathematics of how to detect this corticomuscular coupling or coherence. So you can see that we basically calculate the cross correlation here, cross correlation between the two signals, X and Y, where SXY is the cross power spectrum, cross power spectral density of X and Y, and S and the SXX and SYY are the auto spectrum density of X and Y. So as you calculate all these coefficients, then you put them into this formula to get the corticomuscular coherence estimation. And not only that, after calculating this coherence, you also need to calculate the confidence level of this coherence, which is used by which is done by this formula here. And you can see an example here. So if you want to achieve 95% confidence level, then you need to go beyond 0.19 value for this corticomuscular coupling. And the typical range is between 0 to 1 with the highest coupling between the two signals. Next, this is a description of different steps which you can follow while calculating this band power correlation. So this is a different technique than coherence, which is described in the previous slide. And the reason why we are designing this this new technique is that the traditional coherence-based techniques cannot actually give high accuracy in terms of signal classification. So what we did here is we processed the raw EEG and raw EMG signals, the brain and the muscle signal, through several steps. So such as, first of all, we have done the bandpass filtering between 8 to 12 Hz and 30 to 50 Hz. Followed by that, we squared the signal to extract the band power. And then we have done some moving window average on the signal to get smooth variation upon the signal. So corresponding to each step, you can see the signal modifications in EEG and EMG. So from raw EEG to this smooth EEG and EMG. Then we applied the traditional Pearson correlation here on these two smooth signals, and we calculate the band power correlation between them. So this is a typical experiment to compare the performance of the coherence and the correlation based methods. And we acquired the same signals from the brain region and the hand region. And then we applied this CMC and BPC separately and tried to figure out how much accuracy we can achieve. So you can see here there is a stroke patient in the right hand side figure. And there are some electrodes on his hand and some electrodes in the brain. And he's looking at the computer screen while we are collecting the signals from his hand and brain. So here are some results we have got. So if you see the graph in the right hand side, you can see that the performance of this BPC technique or this correlation based technique is much higher than the coherence based technique, which is CMC H1 and CMC P1. So we experimented with both healthy and patients. So H2 or H1 are the healthy subjects group, and the P is the patient group. So you can see that there is a significant rise in the classification accuracy while we are using this band power correlation. Next, there are some techniques for spatial filtering of these signals also, because these signals are very non-stationary, means their probability distribution changes throughout time. So when we start recording and by the time we end recording, the data distribution also changes. So what we do here is we apply some kind of spatial filtering which minimizes this kind of non-stationarity in the brain. So this methodology goes as follows. After we gather the Eeg signal, we basically try to compute some matrix called W matrix, which is also called CSP projection matrix. And how we calculate is that we take the signals spread across different channels, and there are a few linear algebraic methods to calculate this matrix W, which is then multiplied with the existing data, the existing sensor space, to transform this original raw data into a surrogate sensor space, which is called Z. And after we shift this signal to the Z domain, we basically we are able to select some rows and columns from it. So out of this W matrix, which is called the CSP projection matrix, the rows of W are called the spatial filters, and the columns of W are called this common spatial pattern. So basically, we don't take the entire W matrix. We take specific rows and columns, first few rows and the last few rows of W, to calculate this signal Z. Sorry, to calculate this signal Z, and after calculating the Z, we take the log variance of this signal using this formula here for log variance to basically extract some features out of it. Okay, so as we take these features for different types of motion, so suppose left hand motion versus right hand motions, so and we plot these features on a Cartesian coordinate system, we can see that there is some specific distinction between these two signals. So these round symbols and these plus symbols basically shows the difference between the features between left and right. And there is this classification boundary you can see in blue and red. So these are the distribution of features in two different frequency bands, 8 to 12 Hz and 16 to 24 Hz. So after this feature extraction, we use these features to some kind of signal processing algorithms like support vector machine or neural network to basically take a decision whether these signals are corresponding to left hand or right hand motion. So after discussing about these EEG and EMG signals, there are some other techniques to control the hand exoskeleton, which are basically reading the force sensors inside the finger cap of these hand exoskeleton. So you are seeing the assistive device, assistive robotic device in the patient's hand, and there are some sensors inside this fingertip, inside the fingertip of the exoskeleton. So what we do is that we take these force signals, which are physical action generated by the patient, and we try to figure out whether the patient is trying to open or close their hand. And as they cannot complete that motion, they can only start that motion, but they are not able to finish that motion. That's why this exoskeleton do the finishing task for them. So if you see this video, you can see that the exoskeleton hand is basically opening and closing the fingers of this patient. So it's gradually opening and gradually closing. So this experiment was also done in Kanpur, in the Regency Hospital. Okay. So this is the architecture of the algorithm which we use typically for this application. So this algorithm has two parts. One is called active non-assist mode and another is called passive assistance mode. So it starts from acquiring the signal, force signals from the human fingers, and then we calculate the net force. So that the force is applying at the right hand, at the opening side or the closing side, like flexion and extension. And then we see whether this force is above a particular threshold force. And if it is above a particular threshold force, then we use some optimization algorithm using Levenberg-Marquardt rule. And what we try to do here is to estimate optimized motion parameters for the exoskeleton. So exoskeleton needs, exoskeleton means the robotic hand. The robotic hand needs some motion parameters like position, velocity, acceleration, etc. And those parameters are generated by this optimization algorithm here, which optimizes the force along with these different motion parameters. And there are some impedance parameters called mass and damping coefficient, which we try to optimize. Then there is another mode called passive mode, which is basically indicates the failure to perform that motion. And when we detect a failure in performance of that motion, we drive the exoskeleton with some constant velocity. So, and these patients can be can switch between these two modes anytime while generating more force in either direction. So this is one clinical trial that we conducted on the patients using these technologies. So we used both the EEG based technique and also this force sensors based technique. And we gave them both the visual feedback and the robotic feedback. You can see the visual feedback on this sequence of images here. A person is grabbing the remote control of a TV remote and the corresponding exoskeleton motion. And here we have done the experiment on 5-stroke patients. And these are the description of them, like they are quite old, and they are all in the chronic stage of the stroke, that which means the recovery process has been stopped. And after we intervene with our technology, we have seen some improvements in their hand motion. So this is a typical setup where the patient is sitting with an exoskeleton and a computer screen. So this work has been carried out in Northern Ireland, in Ulster University. So these are some graphs which shows that this coefficient, which we calculated earlier, band power correlation, that gradually increases when the patients do this kind of physical therapy using the robotic hand. So you can see from week 1 to week 5, the coefficient is gradually increasing. And not only this coupling between the brain and muscle is improving, you can see the rise in the accuracy of this system. And also these two measures, which are called ARAT and grip strength, which is basically a test of hand functionality. So how well, these are behavioral measures which we take to check whether the hand is actually improving or not, like they are capable of doing some daily living tasks or not. So in those measures also we have seen some improvement. And these are some typical brain patterns. Like you can see, this is a like diagram of your scalp, your left hemisphere and right hemisphere. So you can see that there are some activations in the left hemisphere, the red zones here, which typically occurs when we do some exercise with our right hand. And last of all, I would like to briefly mention about another technology which we use for brain signal analysis. There is a large facility in Ulster University where me and my colleague Dr. Pramod Gaur has worked. And you can see this source localization techniques, where you can see a diagram of the brain, and in the diagram of the brain you can see that there are some location inside the brain where we get maximum correlation while doing this exercise. And this big machine in the right hand side, it is used to acquire these brain signals. So unlike the EEG, these are the magnetic signals, magnetic field of the generated by our brain while doing some tasks. So you know that any electrical phenomena is associated by its magnetic phenomena. So while the current passes through the neuron, there is also a magnetic field which is generated, and those magnetic fields are very weak, and that's why we use some superconducting sensors. So there are some superconductors inside this big machine which basically picks up this signal. So here we have used the multivariate interaction measure to generate some kind of correlation between these brain signals and the behavioral therapy that we have done in our research. So these are a few publications where you can get some more information regarding our work. And last of all, this is our team at Ulster University and IIT Kanpur, where we have conducted this research, and it was funded by UKRI, UK India Research Initiative and Department of Science and Technology. And lastly, this is our campus at University of Essex in United Kingdom. And this is our brain-computer interface laboratory, where we are all different researchers, postdocs, and professors here at our lab. So these are new facilities that has been built to shield the external electrical activities. These are called typically called the Faraday cages, so that we can take the signals in a noise-free environment. So thank you all for having lots of patience to listen to my talk, and I would be happy to answer any query if you have.
Thank you, Dr. Anirban, for
Thank you very much.
such a nice talk.
Thank you.
Now it's time for the query session. Number of participants has given their questions in the chat box. And now I would like to invite Dr. Vivek and Dr. Rishikesh. They will handle the query session and put up the questions from the audience side. Dr. Vivek, Dr. Rishikesh, please.
Thank you so much, sir, for your valuable input to this memorial lecture. I have received a query from the participant. May I ask the first query, sir?
Okay. Thank you so much, sir, for your valuable input to this memorial lectures. We have received the query from the participants. May I ask the first query, sir? The first query is, what is the transfer function of a neurofeedback network?
Okay, so there is, so as you see that in control system, there are some typical transfer functions, which we know, but here you cannot model the entire system with a single transfer function. So what we do is that we use some signal processing techniques step by step. So the very first step which you can do is that after the acquisition of these EEG or EMG signals is that you apply some bandpass filtering. So you may have known about the Butterworth filters or Chebyshev filters. So typically a fourth order Butterworth filter is used to break these signals into different frequency bands between 4 Hz to 40 Hz. And after you break these signals into different frequency bands, then you should apply the common spatial filtering technique, which I have discussed earlier. So calculating the CSP projection matrix W and then transforming the signal into some different vector space. And after that, you need to select some features out of it. Typically the first and last features of it, and you can form the feature vector. So after that, you need to feed all those features into a machine learning technique. So suppose neural network based technique or support vector machine based technique, and then you will be able to classify those signals. So it's not a straightforward transfer function based approach which we typically see in the control system.
And the second query is, what was the error rate in your multi-model, sir?
Okay, so if you see the error rate, right now it is around 20%. If you design a very good BCI, so it is not 2-3% as you say, because these signals are very non-stationary. So unlike the image signals, which can be distinguished by visual inspection. So suppose if I show you an image of a cat or a dog, you can easily distinguish between these two images. But by looking at these signals, you cannot actually visually distinguish. That's why the error rate is still very high. So that means that there is a lot of opportunity for new research and new algorithms, new techniques that I think as many of you are mathematicians and statisticians, so you can come up with new mathematical and computational modeling techniques to reduce this error. So currently the error rate is around 20%, and we are in a process of minimizing it further so that it come down to 2-3% and be practically used in our society.
And the third query is, sir, how do validate the mathematical model? Sir?
Okay, so for validating the mathematical model, we first of all acquire some ground truth. So we show them some stimulus, like the stimulus of a left hand or a right hand, and then we label those trials. So the experiment is divided into several trials of 10 seconds or 8 seconds, and all these trials are labeled as left or right. So there are two different classes, say class 1, class 2, or sometimes there are 4 classes, like 2 hands and 2 feet. Okay, and after we label those signals, then we go for predicting those signals using our online algorithm. So our algorithm or our neural network or other machine learning algorithms does some prediction on this data, and those predicted labels are basically compared with the ground truth which occurred earlier. And then we calculated different parameters like the kappa value of this signal of this prediction, or the accuracy. There is also a measure called sensitivity or specificity, area under the curve. So there are a lot of parameters by which we can validate the strength of this computational modelings.
And the last query, sir, can we use the optimization technique to optimize in your model, sir?
yeah, like as you see that there are only 2 parameters to model and limited number of data. So we have used a very traditional optimization approach that I have told you, the Levenberg-Markert method, which is very commonly used in many techniques. But then there is scope of some other sophisticated methods also. But for that you need to collect more richer data. Because always there is a scope of integrating different sensors. Okay, so here we have used only 4 sensors. Now you can use some other kinematic sensors like the inertial sensors, or you can also fuse the EMG with it. So when the richness of the signal grows high, you can add more sophisticated optimization techniques to get the impedance parameters.
So thank you so much, sir, for your valuable inputs for this memorial lecture.
Thank you. Thank you very much.
Thank you very much, Dr. Anirban. Not only your talk, but the questions that you have answered, definitely they will provide very broad prospect of thoughtfulness and the research. Now we have with us Professor Odi Makinde from South Africa. I would like to introduce first Professor Makinde. He is a distinguished professor of applied mathematics and computations at the Faculty of Military Science, Stellenbosch University, South Africa, and visiting professor in several international universities. Before joining Faculty of Military Science, Stellenbosch University, Professor Makinde worked as Director of Postgraduate Studies and the founding director of the Institute for Advanced Research in Mathematical Modeling and Computations at the Cape Peninsula University of Technology, South Africa, from 2008 to 2013, and professor and head of the Applied Mathematics Department at the University of Limpopo, South Africa, from 1998 to 2008. Professor Makinde is the recipient of the 2014 Nigerian National Honor Award titled MFR for his outstanding contribution to mathematical sciences and technology by His Excellency, the President of Nigeria. He is Fellow of Papua New Guinea Mathematical Society and winner of several awards, namely NSTF, NRF, TW Kambule Senior Researcher Award, AU Kwame Nkrumah Continental Scientific Award, and SU Chancellor 2019 Award. The International Academy of Physical Sciences, Allahabad, has honored him with the Fellow Award of IAPS in 2017. He authored 4 textbooks and monographs on particle mechanics and incompressible flow theory, edited 10 advanced research textbooks on heat flows in fluids and solids, and published over 500 research papers in many reputed international journals. His present H index is 58, citation index is 13,737, and I-10 index is 278. His research covers a broad range of topics, including fluid mechanics, nanofluid dynamics, heat and mass transfer, hydrodynamic stability, dynamical systems, biomathematics, and epidemiological modeling, combustion theory, computational mathematics, and improved perturbation techniques. He has taught, supervised, and mentored several students at undergraduate, postgraduate, and postdoctoral levels. So, let me join to invite him for his talk. May I request Professor Makinde?
Thank you very much for the kind presentation. Kind introduction. Let me start also by thanking the organizers of this memorial seminars, webinar, for taking it, for making it possible for me to share some of my research work with my colleagues. And as you know, Prof. Sharma is my friend. We knew each other, and I really want to thank God for his life, because Prof. Sharma, Prof. P.R. Sharma, I can call him a man with excellent level of humanity. He's a man who loves humanity and a man who is highly professional. He's a highly professional man and a man of high integrity from my point of view and my relationship with him. So I wish his family a very pleasant pleasant life after the demise of their loved ones. I pray that God will continue to secure them and uphold them. So back to my talk. As you have seen the title, Computational Modeling of Automobile Catalytic Converter Operations. The other point I want to share also is to make us realize that it is the grace of God that makes us to be able to communicate even in this global pandemic, because I'm talking right now from South Africa. And as you know what is going on around the world, we thank God for giving us this platform to share knowledge, despite all the disruptions in academic activities all over the world. We still find it a platform like this to share knowledge and talk about academic and research work in order to improve the condition of life. I chose this topic because I know Professor P.R. Sharma, he loves mathematical modeling. He's a man who enjoys modeling physical problems in order to improve the condition of humanities. So the title, as you have seen again, is Computational Modeling of Automobile Catalytic Converter Operations. My talk will throw more light on how we can use mathematics to improve the operation of engineering systems, engineering devices, such as catalytic converter and other engineering devices. It also throws more light on how we can model problems, how we can use application of mathematics to improve science and technology. Now, the outline of my presentation, the overview is as follows. Talk about introduction, application, literature review, fundamental equations involved, model formulations, numerical approach, numerical results, conclusion and references. Now, as you have seen in the world today, you will notice that millions of cars on the road are a source of air pollution. The amount of pollution that all the cars produce together can create big problems. Government create clean air laws that restrict the amount of pollution that cars can produce in order to solve this problem. Automakers and engineers have made many improvements to car engines and fuel system to keep up with this law. In 1975, a very interesting device called a catalytic converter was invented. Catalytic converter, as you all know, We say it's a converter. It's a device to reduce or to convert harmful pollutants that automobile inject to the environment. It converts it to less harmful emission. So it converts what can damage people's health, human health, what can damage the environment. It converts it to make sure that by the time they get to the environment from the car through the exhaust pipe, they are less harmful. That is the work of this catalytic converter. In short, the aim of it is to reduce air pollution and also to enhance the safety of lives and properties. That is the aim of this catalytic converter. As part of introduction, before you model a problem and you improve its efficient operation, you must first know the physics of the problem. And I'm explaining now to you the physics of the problem and try to model and to improve its efficiency using mathematical theory and concepts. The exhaust in automobile consists of 6 ingredients. The exhaust of automobile consists of 6 ingredients. 3 of them are, which is number 1, nitrogen gas, carbon dioxide, water vapor. They form the 3 which come from the exhaust as an exhaust from a car or automobile. And these 3 exhausts, they are less harmful to human and the environment. That is nitrogen gas, carbon dioxide, and water vapor. Why? Nitrogen gas is needed by plants. Plants use it. Carbon dioxide is needed by plants for photosynthesis. Water vapor is needed by human and by plants. So all these 3 do not damage the environment. But the other 3 ingredients of car exhaust is carbon monoxide, hydrocarbon, and nitrogen oxides. These 3 components, they are very harmful to human and also very harmful to the environment. For instance, carbon monoxide can cause death if you breathe in carbon monoxide. Also, hydrocarbon is very, very bad in terms of issue of ozone layer. It depletes ozone layer and causes what we call global warming. And we have nitrogen oxide, which is also very dangerous. It can lead to acidic rain, can cause acidic rain, which is extremely dangerous to a human. So you can see that the cars and automobile we are using, if it's not properly designed and fitted with an efficient catalytic converter, then it will create more harm to human and environment than good of taking us from one place to another. So let's go to what is catalytic converter. Like I said, it's a device installed in vehicles and its use is to reduce the toxicity of the emission from the car. And how does it operate? When the fuel, the gasoline we are using in the car is made up of hydrocarbon and nitrogen and all kind of materials. Then, if this fuel is not properly combust, then we are going to have some of the uncombust or fuel that did not combust properly escaping to the environment, which are oxide of nitrogen, which are carbon monoxide and hydrocarbon. That is those thick fuel, very dark smoke that come out of the exhaust pipe. They are hydrocarbons, which are very poisonous and also contain carbon monoxide at the same time oxide of nitrogen. So that will happen if your catalytic converter is not designed properly. And this is where you fitted, it is fitted around here in the car. So you have a pipe. When the fuel flow through the pipe, it has to pass through here to completely burn. Now, most vehicles used, most commonly used motor vehicles, exhaust system, always have this converter. And in this converter, two things take place. There are reactions that take place there, which enable those uncombust fuel to be completely combust. Let's look at the component of catalytic converter. Like I mentioned, physics of the problem need to be looked at properly. The converter consists of several components, but the core of the components of the converter is what we call a ceramic honeycomb. It's like a porous media. The design is a ceramic, but it's designed like a porous media. Can you see? It can be in form of a cylindrical geometry filled with porous media, which in form of a honeycomb. That is, you see the honeybee. The honeybee, like a comb, you can see small holes designed this way, through which the fuel can flow through. So you can have a honeycomb catalytic converter. So it's designed in this way. Or you can have it in form of a stainless steel. You can have a stainless steel in form of a put together in form of a porous media. You see all this like a porous media. So, and the catalytic converter is designed this way for a purpose. And you will see in the model why it is designed like that, why it's all designed to be improved as well for efficient operation. Now, so you can have a metallic design catalytic converter made up of this honeycomb stainless steel or honeycomb ceramic, like filled with porous media. So those are the points we need to take note in the physics of the problem. What of the structure of the catalytic converter? If you see a catalytic converter, it's composed of this. You see the fuel or your gasoline that goes through the converter contain hydrocarbon, carbon monoxide, and oxide of nitrogen. They go in this way. They flow through the converter through this way. And the outcome we wanted is water vapor, carbon dioxide, and nitrogen, which are less harmful. But if this converter is not working properly, then there is tendency that hydrocarbon may escape and come out on the other side. Instead of having carbon dioxide or water vapor. Or you can see that oxygen of nitrogen may escape. So if this converter work efficiently, all this will not happen. The byproduct or the outcome will be here. Inside the converter, you have these two ceramic honeycomb or porous media, call it porous media. ceramic honeycomb made in form of porous media. Or you can also have a metallic stainless steel honeycomb porous media like this. It's a porous media design with small pore spaces. You can have it here. Now, you can see that inside these two components, inside this compartment, two things takes place, two reactions. You can see the fuel will flow. There is a flow of fluid, which is the fuel taking place, and there is also a chemical reaction taking place, chemical kinetics, as it's flowing through this porous media. So when you are designing it, you are modeling it, all this has to be taken into consideration. For instance, you can see this one is like a cylindrical porous media, a cylindrical geometry filled with porous media. All the geometry of the system also need to be taken into consideration. That's why the physics of the problem is very, very important to understand how it is, and before we go into modeling and how to improve the design. Now, inside here, two things takes place, like you see here. You can have what we call a three-way catalytic converter, whereby you have what we call a reduction and oxidation reaction. As the fuel you have here, you will see that here, as the HC, hydrocarbon, carbon monoxide, oxide of nitrogen flow through here, they go through this porous media. And when they go through, they come out here as nitrogen also. When they go through, oxide of will be reduced. There will be reduction reaction. The chemical kinetics taking place will be reduction reaction here that will reduce oxide of nitrogen to oxygen and nitrogen. That's reduction reaction. Remember, this reduction reaction is very, very exothermic. It produces heat. This chemical kinetics for reduction is exothermic. It produces heat. That means heat will be generated inside here as this fuel is flowing through it that contain all this unburnt fuel. Also, there is oxidation reaction. The carbon monoxide in the fuel will be oxidized to become carbon dioxide because oxygen is released here during reduction. This is oxidized carbon monoxide to become carbon dioxide. This oxidation reaction also is very exothermic, which means it releases heat. That means inside here, a lot of heat must be released. And also the hydrocarbon, the unburnt fuel, the hydrocarbon also, they be oxidized to become carbon dioxide and water vapor. So the hydrocarbon will be oxidized, carbon monoxide will be oxidized, and nitrogen oxide will be reduced. Both reduction and oxidation reactions are exothermic chemical kinetics. All this must be understood. The chemistry that takes place and the physics of the system, all this need to be considered when you are doing the mathematics in terms of modeling of the system, in order to enhance the design and to improve the efficiency of such engineering devices. Now, let's go to modeling techniques. We have completed the introduction that deals with the physics and chemistry of what we want to apply mathematics to in order to improve the efficiency. The modeling techniques, just to summarize it, you need to follow 7 steps. Step 1 is your problem statement. What is our problem statement in this case? We want to improve the efficiency of autocatalytic converter. And the problem is because many vehicles are fitted with it, but they still inject pollutants into the environment, which means the catalytic converter they have probably is not working efficiently or effectively to produce desired results, which means some of the unburnt fuel containing nitrogen oxide, containing carbon monoxide, containing hydrocarbon can still escape. So not all of them, few of them can still escape and still create pollution to human and the environment. So the aim is to reduce that or to eliminate that. That is the problem stated. Then you have to draw the diagram of the problem, schematic diagram, to simulate. You sketch the diagram of what you want to model under some reasonable and physical assumptions, which actually take into consideration some of the major features of the device you want to improve. Then you need physical law. What are the physical laws involved in this situation? You have fuel flow. There is a flow of fuel. That is the geometry, which you see here. The fuel that flows through it is a fluid. You know, fluid means anything that can flow. So fluid dynamics is involved in this issue because there is a flow of hydrocarbon, carbon monoxide, nitrogen oxide. They are gas, they are in form of fuel, which is gasoline, which you buy, the petrol, you buy, the gasoline, they are involved. So, which means there is a flow. Fluid mechanics is involved. Also, the geometry of this of the system. Geometry of the system is a porous media. Porous media. And if you look at it like a cylindrical body filled with porous media. And inside there is what you call chemical kinetics, exothermic chemical kinetics taking place. All these are the physical law which must be incorporated into the model for you to get a desired result. Property must be taking place. The fluid, what are the properties of the fluid? So that whatever assumption you are making must take care of all this, and the mathematics must take care of the physical law. Then you do the calculation, which is going to be a computational method, because some of the model you will get will be highly nonlinear. And when they are highly nonlinear, you have to employ computational techniques, numerical techniques, based on the type of problem you obtain at the end. And again, you solve it. There can be verification. You can verify your results either by looking at what experimental result obtained or by looking at the literature, what is already there, whether your results under some conditions agree with what's already there in the literature and what are the improvements you have put into it to add to knowledge, that is to add to already known knowledge in the literature. So, and discussion as well. So these are what's needed when you want to model problems for engineering use or for scientific use. And also, I put a diagram here. When you model a problem, you don't go through a very steep gradient, steep slope. You start here, you want to go straight to the solution here. You don't pack everything in the problem into your model. Otherwise, your model may be too cumbersome, too difficult to solve at initial stage. Although it can be done if you have all the mathematical techniques that can deal with highly complex situation model. But you can also start by going through a less steep slope. By you model it, you put realistic assumptions, and you are improving it gradually until you get to the solution. When you get there, you improve it, so that you have a continuous improvement on your model. When you get the result, you add some, and the more you improve your model, the more complex it becomes, the more mathematical and computational techniques you needed to tackle it, and you continue to move. And that is very encouraging. And that is the recommended approach in tackling both scientific and engineering problems. Not that the result you get here will not be, it will be very useful. The only thing is that there may be some little things you did not include. You include it, then you improve it again, you solve. It will improve your result. You solve, improve your result until you get the perfect result you desire at the end. So that is a way to deal with both engineering and scientific problems in terms of mathematical modeling. Now, let's go to mathematics. The mathematics involved in this model, like I mentioned, about the physical law, which is this part's physical law in general, is continuity equations, because fluid is involved. You need fluid mechanics. And you have the continuity equations that deals with the conservation of mass. In this case, we assume that our fuel, which is flowing, is incompressible fluid. That is, the density is almost constant. The density of the fluid that is flowing is almost constant. So if you assume that, we can take our continuity equation as divergence of velocity vector to be 0. We also have the Navier-Stokes equation. In this case, we assume that our fluid is Newtonian and it satisfies Newton's law of viscosity in terms of the constitutive equation, the relationship between the shear rate and the stress, the shear and stress. So we assume that the relationship is linear relationship, which is Newton's law of viscosity. So we have Navier-Stokes equation, which is what we call the momentum equations. Momentum equation. And we have a body force here, a body force, which is attached to it. This body force is due to the honeycomb porous media. If you look at, because of this thing, which is in the geometry, this one. And this term, you can call it a body force. Where K here, capital K, is the permeability of the honeycomb porous media in the catalytic converter. And also, this term, C, is the inertial term due to the nonlinearity of the porous media that filled the that constitute the honeycomb because of nonlinearity in it. So the inertial term is due to what we call Forshimia term, inertial term of porous media, which is you can see it's U squared, the nonlinear resistance created by the porous media. And this is the linear resistance, which is due to Darcy porous media term. This nonlinear resistance due to Forshimia. So we assume both linear and nonlinear resistance are there so that you combine the two. All this is due to the honeycomb, either made of ceramic or stainless steel, which filled in the catalytic converter where those operation takes place. So that must be included in your model as your body force. And also, because of internal heat generation in the system, which create combustion, then you need energy equation. The energy equation comes from the first law of thermodynamics. So you have this thermal conductivity of the fuel that is flowing through the catalytic converter, the viscous dissipation, and this one is the internal heat generation. Remember, we have the exothermic reaction that is taking place inside the autocatalytic converter, reduction and oxidation reaction. That is this term. Remember, this term is there. Therefore, you need to take this term into consideration when you are modeling this type of problem. It's extremely important because it will tell you not only physical dissipation or also the porous media resistant term, heating term, because the parts of porous media, there is a term here also which will be included. It's part of dissipation, but again, it's porous media resistant. All these are internal heat generation will be added apart from the chemical kinetics, exothermic chemical kinetics. Also, you know, you can also include the concentration of the fuel, the amount of the fuel. You know, when you drive your car, you burn fuel, the fuel quantity reduces as is being burnt, as the catalytic converter is combusting them to reduce them, then you are having reduction in the fuel. So you can see that, and this one can be a destructive reaction due to the combustion that generates heat, and heat is what added here. So you can add all those. So the major thing to put, you have the quantity equation, the Navier-Stokes equation, conservation of mass, of momentum, conservation of mass, conservation of energy. All these are physical laws. You need to incorporate into your model. Concentration equation, you need that, and also the chemical kinetic equation. In chemistry, which is the chemistry of the system, the exothermic chemical kinetics is represented by Arrhenius equation. Arrhenius equation in chemistry represents exothermic chemical kinetics, which means as the reaction increases, the rate of heat generated, the temperature also increases. So this is represented by this. And you can, where this A is pre-exponential factor. Remember, Cp is the specific heat and constant pressure, and also all this T is temperature, U is velocity vector, and all this are there. Mu here is the dynamic viscosity of the fluid. You understand? This is diffusivity of the fuel as it's moving through. And yes, so you have all these things involved. And K is the reaction constant, but your reaction constant can also be a function of temperature and whatever. So Arrhenius kinetics is extremely important when you are dealing with exothermic kinetics. So which will help you to know what to put here and what is taking place while this fuel is being destroyed, is being removed, decrease. But in this model, which I'm going to present, I will assume that the fuel is constant. In the amount of fuel is constant, which means you can assume to start with is constant, then you can improve it further and say it's not constant, the fuel is being decreased, the more fuel it takes, the more it generates, and so you can do a lot of improvement in model. So let's look at the model. This is the model problem. The model problem we have here in terms of the geometry is this. You can see the model problem. So the model problem here is such that it tells you a kind of exothermic reaction taking place and fuel being burnt in the system. So you can see what is taking place as the fuel is flowing. The fuel flow through here, exothermic reaction take place, and there is a resistant heating due to the porous honeycomb, and the amount of heat generated inside is enough to create combustion. Combustion take place inside, and what is coming out here now will be what will contain carbon dioxide, nitrogen, and also water vapor, because this combustion enhances complete combustion of the fuel due to reduction, enhances reduction and oxidation reaction to be complete, so that none of the burnt fuel escape through the exhaust pipe to the ambient. And that's what we have here. Reduction, you have this, you have oxidation. So you can, some of this work, you can see it in the paper published in the volume 29, Applied Thermal Engineering 2009, and some of other work I published later in this area of autocatalytic converter. You can find them in several journals under Science Direct. You check, you can see so many work of mathematical modeling, how to improve the operation of autocatalytic converter. Now, in the model, this model, the assumption is that you have constant amount of fuel, which means we don't involve this. But in this concentration equipment, we involve that the heat generation is involved in the model, which is reasonable. And the flow is steady. We have it's two-dimensionally compressible. The first cylindrical pipe, due to the geometry of the system, and the pipe is filled with porous media, and inside it there is reduction and oxidation reaction taking place, which is represented by the Arrhenius equation, Arrhenius reaction. This equation comes from the momentum equations, which is what we have here from Navier-Stokes. Here, the one we have here comes from it in dimensionless form, where these two terms results from the honeycomb porous media, which you have there. Beta here is the inverse. It's called the shape factor, the inverse of the Darcy number, which is the linear resistance of the porous media of the flow through here, and S is the non-linear resistance due to porous media, which is called Fukushima parameter. A here is the pressure gradient that is pushing the fluid as it's flowing through this catalytic converter. So you can see as the fluid is flowing through, reaction take place, but you want this reaction to take place very quick. Also, the body of the catalytic converter, the environment, must be partially insulated in a way with material that will not allow the heat to escape. Because if the heat generated escape to the ambient environment, there is tendency that this combustion may delay, and you are not going to have effective or complete combustion of the fuel. If you see that if this takes place, I mean, if you have the escape of heat, if the Nusselt number, that is the rate of heat loss to the ambient, is very high, then you are not going to have complete combustion. You want more heat to be conserved inside this converter to make sure that it leads to thermal runaway inside. The thermal criticality value is reached, and the combustion can take place, and this will come out, what we want. This one is from energy equation. Lambda is called the reaction term, the reaction parameter, lambda. And it's also related to what we call Frank-Kamenetsky parameter, which is due to the chemical kinetics that take place in the system. The Arrhenius chemical kinetics. So the increase in lambda means increase in reaction rates that take place, exothermic reaction, oxidation reaction. BR is the Brinkmann number, which is a product of the Prandtl number and Eckert number. Brinkmann number tells you the contribution of the viscous dissipation due to the flow, the shear rate of the fuel as it passes through the catalytic converter, and also the honeycomb resistant heating, beta and S. This honeycomb resistant heating, they all add together with viscous dissipation to contribute to the additional heating in the system. So increase in BR means increase in the internal heat generation due to viscous dissipation shear rate, and also due to the resistance of the honeycomb porous media. Why this one the internal heat generation due to chemical kinetics that takes place, the Arrhenius chemical kinetics, and the geometry is cylindrical. That's why you have the Laplace from it to be of this nature. So this is dimensionless. The boundary condition, we assume axis symmetry. The fuel is flowing through here, axis symmetry, which is at r equals to 0, which corresponds to eta is 0, and r equals to 1, which corresponds to eta equals to 1. Then you have it here. And there's no slip condition at the surface. None of the fuel is coming out of the catalytic converter of the surface, but there is heat transfer where you have there is interaction, heat exchange between the catalytic converter and the environment, heat loss. But the rate of heat loss represented by Bout number, thermal Bout number, need to be regulated such that you don't have a lot of heat escaping from the material. If a lot of heat escape, the combustion will not be complete. So all these need to be regulated to achieve desired result. Now, this mathematical problem, this equation we have here is a mathematical problem, and it's non-linear. It is boundary value problem. At this stage, you are now, physics of the problem has ended, is now mathematics. To solve this mathematical problem, because of non-linearity, you can see W squared, which you have here, which is velocity, this temperature variable, this velocity variable here, which you have here. Now, and this also is non-linear. You can have theta e raised to power theta 1. So these are non-linear and they are coupled, because you need to know this for you to find the exact solution of this problem or analytical solution is not feasible. Therefore, we have to use computation. We have to use numerical method. Numerical method you can use here to solve this problem can either be finite element method can be used. Finite difference method can be used. You can use any method at your disposal as long as your method, or you can use semi-analytical method, semi-numerical method. For instance, there are methods like variation iteration method, which are semi-numerical method. Homotopy analysis method can be used, which are semi-numerical method or semi-analytic as well. And you can also use Adomia decomposition. All these are approximation method, which are semi-analytic, semi-numerical. But pure numerical method will be more efficient in this case. But again, you have to look at your degree of accuracy of the method you are using. So this is extremely important. Therefore, we have solved this problem. We use shooting method, which is a form of I've already described all the parameters involved, which are dA' number, beta shape factor, pressure gradient. You have this porous media, Brickman number, this exothermic reaction parameter, flank, which is Kamenetsky parameter, Bout number, activation energy parameter. Nusselt number is defined in this way, telling you the rate of heat loss to the ambient. Skin friction, the rate of shear rate, which is non-dimensional shear rate, and the surface, inner surface of the porous media. I mean, of the catalytic converter, inner surface of the catalytic. So you can have the shear rate. So with skin friction. So you have all this done. Then I told you we solve it numerically using shooting method, which means you convert the boundary value problem to initial value problem. But when you do that, you are going to have unknown initial condition, which is T1 and T2, because you have converted the boundary value, because you have the value at the center of the pipe, which is axisymmetric, and at the surface of the center of the catalytic converter, and at the surface at eta equal to 0 and 1. Then we convert everything to 0 at 0. There are two unknown initial conditions with T1 and T2. These two unknown, you can obtain them using what we call Newton-Raphson method. Newton-Raphson method is a method of determining the roots of a non-linear or linear or non-linear problems. Then you can use it to determine the roots, and that root will be your initial condition by a method we call shooting. You shoot and use Newton-Raphson to get the initial condition. When you get the initial condition, then you can now solve this problem as if it's an initial value problem. This very problem, you can now use longitudinal feedback method or longitudinal of order 4 or order 5, higher order longitudinal method to solve it. Because longitudinal is a finite difference method, but of higher order accuracy. It's a numerical integration. You can integrate it numerically and get a very excellent result which is accurate. You can also use finite difference. If you like, you can use finite element, and all of them will give you desired results. And you must test the accuracy of your result as well. But remember, all numerical methods are approximation methods. It's an approximate solution, not exact solution. And we are using them because we cannot find the exact solution, but we can find very almost very accurate, almost accurate to exact the numerical results. And some of the methods are already there, which you must be cued with. So we tackle them. These are the solutions. The solution we obtain is this. You can see this graph. This graph shows you the heat transfer rate, Nusselt number, against lambda. Where these points, which you have here, is where thermal criticality takes place. You can see bout number. As you are increasing bout number, which means you are increasing the rate of heat loss. You can see as you increase BI, the rate of heat loss at the surface to the ambient, you are increasing it. If you increase the rate of heat loss, that means less heat will be conserved inside the catalytic converter. Then you are not going to have complete combustion. Then you are not going to have your catalytic converter working operating efficiently. Then you still have dark smoke coming out of your exhaust pipe. You have dark smoke because there will not be combustion taking place completely. So that is a problem. So you have to reduce that. What does the result tell us? It tells you that at very low, when bad number is 1, you have the combustion lambda C, which you have here, is at 0.552. You have it here. But when it's 10, when you increase the heat loss, the rate of heat loss at the surface of the converter is high. You can see this. That means it takes longer time to have combustion here. Because the rate of heat loss will be very high. Nusselt number is high. The heat loss to the ambient is high. You can see for this blue, and it stop here. At this point, above this point, there is combustion. That means you have to reach lambda C. The reaction rate has to reach 1.629. Maybe 1.7. Above it, the combustion will start taking place. Fuel will start burning. Therefore, you see that you have to reduce it to have combustion very. So when you reach maybe 0.55, when you reach 0.6, you just see combustion taking place. There will be complete combustion before the fuel start going out. Remember, this have to take place within a second or 2 seconds. So you have to reach combustion thermal criticality value very early. So increasing, if you are not having catalytic converter working properly, you have this problem. But Brickman number, increase Brickman number enhances combustion. You can see lambda C, you reach them early. 0.5, 0.4, 0.3 as you increase the Brickman number. Due to the contribution of the porous medial cup and also physical dissipation, you can see it enhances combustion because it enhances attainment of criticality value above which combustion takes place. The same thing we check for other X and E and all those things. So these are, I just put the graph here to represent them. You can see here, as we increase S, you are decreasing the permeability. Increased S means this is the nonlinear inertia. You are decreasing the permeability, which means you also decrease the Nusselt number. You decrease heat loss. And when you decrease heat loss, what are you doing? You are enhancing combustion. More heat will be conserved, and you can have more combustion taking place, which is also represented. So that is the advantage putting that. It also decrease beta. Beta is the increasing beta means you are decreasing the linear resistance. I mean, you are increasing linear resistance. That is, by increasing beta, you are decreasing the pore spaces. The pore spaces will be decreasing. Therefore, you also reduce the heat loss to the ambient. So increase S and beta reduces the Nusselt number and enhances attainment of thermal criticality, which enhance combustion in the system. Friction also reduced. Anyway, we see that friction is reduced. We observe that, which is very interesting because we are dealing with fuel in this case, and there is combustion taking place because of that, making the fuel to be light. And what's coming out now will be desired gases, which is carbon monoxide, water vapor, and nitrogen. Okay, the profile as usual, you can see this is the beta. We know that beta and S will decrease the velocity profile because of the obstruction of the resistance to the flow. So the velocity as expected, and also the pressure gradient, increased pressure gradient, the flow through the pipe, then you can see the velocity increase. The same thing with temperature, because when the flow rate increase, dissipation between shear rate will also increase. Interaction due to physical dissipation increase, then you can also see temperature increases. So all these are the results we obtain. But let me go to conclusion because of the time. An exothermic reaction thermal criticality value lambda exists, above which no real solution can be found in terms of mathematics. The fuel flow becomes thermally unstable and thermal combustion takes place. For exothermic reaction within the value of 0 and lambda c, then the flow will be thermally stable. No combustion will take place when you are within this. You have to be above lambda c to have that. And what are the parameters that reduces the value of lambda c so that you get it early? The parameter is BR. Increase in BR will lessen the value of lambda c. But if you increase BI, epsilon, all these they will increase the value of lambda. So you have to increase BR to enhance the lambda to enhance combustion. Fuel velocity is enhanced with pressure gradient and also diminished with this S and beta, as we know, because the cost of obstruction. Fuel temperature rises with Brinkman number because of physical dissipation and the porous media, and the lambda. But this lambda is the reaction rate, but lessen with this, which we have the loss of heat to the environment. Both skin friction and Nusselt number are decreased with a rise in S and beta, but Nusselt number increases with what we have here. In order to enhance the efficient operation of autocatalytic converter, appropriate regulation of this embedded parameter must be incorporated into the design. This parameter must be regulated properly to get desired result in the design of it. This will facilitate complete combustion of onboard fuel and eliminate air pollution due to automobile exhaust. Finally, the catalytic converter is a great thing to have in a car because of its ability to help save the environment from those harmful gases. So the issue now is that if you see the model we have here now, to as a comment, like I mentioned, look at this model. One can go back again and improve it by assuming this rate constant is a function of temperature, and you can now also function of concentration and include this concentration equation and see how your fuel is reduced, how this is improved. You can also look at it as fuel as non-Newtonian fluid, which means there are a lot of improvement, but the result will not be too much different from what we are getting. But the only thing is that it will improve the understanding of the system and the design. So those are the comments I make there, and these are references which you can find. Thank you very much for the patience you have taken to listen to my talk. I'm very grateful for the opportunity you have given to me. Thank you very much. May God bless you abundantly. Now it's time for questions. You can have question time whereby you can ask me any question you think you want more clarity, you want me to talk about. So let's go to question and talk about where you want more clarity on the problem. Thank you very much.
Thank you very much, Professor Makinde.
Thank you very much.
Yeah, I would like to invite Dr. Vivek and Dr. Rishikesh to put the questions of the audience. Dr. Vivek and Dr. Rishikesh, please.
Next. Thank you very much, sir, for your valuable input to this memorial lectures. We have received the query from the participant. May I ask the first question, sir? The first query
Yes.
is, what are the potential hazard of the toxic substance emitted by a car without a catalytic converter?
What are questions? Sorry. What
are the potential hazard of the toxic substance emitted by a car without the catalytic converter?
Thank you very much. The answer to that, what are the potential hazards without catalytic converter? Now, to answer that briefly, maybe what I will just do is to show you, can you still see the presentation? Can you see the presentation? Hello?
Yes, sir.
Yes, sir. Yes, sir.
Can you see the PowerPoint?
Yes, sir. I'm sending.
Okay.
Yes, sir. It's live.
You can see it. Can you see it? I want to show you potential hazard is this. Look at the potential hazard. Without that, you will see this hazard, which is very, very dangerous. Potential hazard. You will see that when I talk of the ingredients of catalytic converter, look at the ingredients. If there is no catalytic converter in the car, which means you have a car that does not have this converter. If this one is not there, what will happen is this. You have carbon monoxide going through freely to the environment. You have hydrocarbon going through to the environment. You have nitrogen. Therefore, what is carbon monoxide? You see, carbon monoxide is odorless, colorless gas that can kill. It can kill human being. The safety of life and property will be jeopardized. When you breathe in carbon monoxide in the air, it can cause death, cancer, all kind of trouble. What of hydrocarbon? We are all talking of global warming, global warming, global warming. The hydrocarbon, they contribute problem to what we call the ozone level. That is creating ground level ozone. They make ozone level, they form a what we call smog, a thick black smoke. They don't allow the heat that from the sun to escape. They trap the heat and created into the earth and created global warming. We all know the problem of global warming today. Global warming is causing climate change, causing a lot of things, disaster everywhere, flood, and all kinds of things. So, what of nitrogen oxide? Nitrogen oxide, as we have seen, can lead to what we call acidic rain, acidic rainfall. Acidic rainfall, you know what acidic rainfall? It destroys crops. It can destroy crops when there is rain and the rain is acidic. The crop will be affected, the animals will be affected, so you are drinking poisonous water. So it pollutes underground water. So many things are the cause. So the answer is extremely enormous. Thank you very much.
And the second query is, does the catalytic converter run at the 100% efficiency?
That's a very good question.
Why or why not?
Catalytic converter supposed to run 400%, but it doesn't run 400% efficiency. The reason why it's not running 400% efficiency is because the converter itself, every machine degrade over time. If you buy something today, after some time, as you are using it, it degraded, the efficiency reduced. But what this model is trying to do is that how can we optimize the efficiency? Because there is possibility of escaping of some of the toxic, not all of them, some of the toxic substance in the fuel to the environment through the exhaust pipe. And those are the ones that do not combust properly. And the reason is because the thermal criticality of the reaction does not, we don't attain it very fast. If you do not attain the criticality very early, then and you know its movement, fuel is flowing regularly. So if criticality is not achieved early, it's delayed due to the escape of it to the ambient, or the catalyst is faulty. Then you see that some of the unburnt fuel will come out and will create a disaster. So it's not working efficiently. But what I'm proposing is this, and I know it's possible. This converter could be designed in a way that it can be regularly, all those parameters can be regularly adjusted to make sure that we can always improve the efficiency. So the reason why it's not working efficiently is because of incomplete combustion. It's not working 100%, or also due to degradation of the material over time. Degradation of the material over time can lead to inefficient operation. You have seen many cars in India on the road when they are driving. You just see the thick fuel, thick smoke coming out of the exhaust pipe. They have converter. When you see that thick smoke, that thick dark smoke, shows that the converter is not working efficiently. Although they have converter. So what do we do to that? They have to go and repair the converter or buy new converter. So in many cases, it doesn't work effectively or efficiently, but it needs to be optimized. So that is it.
And another question is, sir, how can catalytic converter be damaged or misused?
How can it be
damaged or misused?
Misused?
Yes, sir.
Oh, it can be misused.
Yes, sir. How can catalytic converter be damaged or misused?
Sorry, you say can it be misused or what?
Yes, yes.
Okay, now catalytic converter can be misused if it's not maintained properly, which means if you have it, you must go for regular, you go to garage. In South Africa here, we call it a garage. You take your car to garage every, maybe just like human body, you see your doctor. Well, you notice that the exhaust in your car is having maybe every 6 months. You have a new car, every 6 months, go to garage, a new car, they check it. When they do the analysis in the garage, they will tell you your exhaust is this, there's a thick black smoke there. Therefore, they will help you to fix the problem. But if you don't do that, you are misusing it, because if you just have a car, 1 year, 2 years, you are driving, you don't check anything, then you are misusing it. Because it's an engineering device that needs to be improved. You go there, they can change it or they can improve and check it, and so misusing of it is very common because of human carelessness. Human carelessness on automobile servicing can lead to misuse of catalytic converter. If you are careless about it, about servicing your car, then you can misuse it, and it can create danger to the environment. And governments all over the world are having this problem. They are trying to make sure that they reduce pollution, air pollution. They want the car to make sure that don't contribute menace to the environment. That is misuse of such a thing. Yeah.
So now we invite to Dr. Alok Bhargav, sir.
Thank you very much, sir.
Yeah, thank you.
For your nice talk and the solution of the queries. Definitely, our audiences and our guests and other participants must enjoy your presentation and get benefited from your thoughts. At the end of this session, I would like to invite Dr. Ruchika Mehta for vote of thanks. Dr. Ruchika.
Thank you, sir. Good afternoon, everyone. I feel privileged in proposing the vote of thanks on this special day of birth anniversary of Professor Pierre Sharma, in whose memory we pay pious tribute by doing what he would have always appreciated and actively participated in. Though his physical presence is highly missed, but his memories and his work will always remain with us. I thank Department of Mathematics and Statistics, Manipal University, Jaipur, for giving me the opportunity to express my gratitude on this special day. A very large number of representatives participated in this memorial webinar, which is a huge success in itself. On behalf of Department of Mathematics and Statistics, Manipal University, Jaipur, I express my heartfelt thanks to the invited guest, Professor P.N. Pandey sir, Vice Chancellor, Nehru-Gram Bharati University, Allahabad. I would like to thank Professor O.D. Makande, South Africa, and Dr. Anirban Chaudhary, United Kingdom, for their gracious presence. I would like to thank our respected Dean, Professor Mukhopadhyay sir, Director, Professor Lalita Ladwani ma'am, HOD Dr. Indivar Kumar, organizing team, and all members of Department of Mathematics and Statistics. I would also like to thank family members of Sharma sir, Madam Savitri Sharma, Dr. Pramod Gaur, Dr. Aditya Gaur, and Anjali Gaur for their kind support and help always. I would also like to thank Professor Mukesh Sharma sir, Jambeshwar University, Hisar, Dr. Surinder Sharma, Dr. Chalan Shukla, Dr. Pankaj Mathur, and all members of Professor Pierre Sharma Memorial Educators Association who were actively involved in making this a grand success. Finally, I take privilege in thanking the conveners, Dr. Kalpana Sharma, Dr. Alok Bhargava, Dr. Rishikesh Tiwari, and Dr. Vivek Singh for their immense efforts put forth in planning and execution of the seminar in such a short time. I would like to conclude by thanking the Almighty, our beloved professor, late Professor P.R. Sharma, for making our efforts shine. One more information regarding certificates that e-certificate will be provided within 5 to 7 days after submitting the feedback form, and feedback form will be sent to all registered participants via mail. Thank you all once again. Have a wonderful day. Thank you so much.
Thank you.
Thank you so much, sir, for your valuable input to this memorial lectures.
Thank you. Thank you. Yes. Thank you.